The circle, the sphere, old friends and familiar equations here derived multiple ways to highlight different integration techniques, but we're going to start with polygons. The more sides, the more circular. A little trig here to find the perimeter, again and again, and then a switch to radians allows us to use the small angle limit derivation number 1. Next, calculus, the line integral, which is not too mysterious. Take any curve, any small piece of it, expressed with dx and dy. Our curve is a circle, of course, so let us use radial coordinates. Wait, why does x equal sine theta? Don't we usually measure theta from here? Well, many times, yes, but this choice moves x from 0 to r as theta goes from 0 to pi over 2, and that will matter more later. Here things cancel out nicely, but we're just getting warmed up. This time we'll stick with x and y, and a new ds worth remembering. This segment, integrated from 0 to r, is 1/4 the circle. But where did that step come from? From the derivative. Hey, a fun fact about the slope of a circle, which I think is also worth remembering. But wait a minute. You said no radial coordinates. I did. And this is a special integral. And if we call this z, then that is dz, all of which is pretty complicated. Lucky for us, the next derivation, using radians, is way simpler. For the area of the circle, we are back to polygons, filling out the area with trig, again and again and again. This time, though, we'll use the double angle formula, followed by that small angle limit substitution thing. Or take all the triangles and line them up half on top, half below to make a rectangle. Or switch to radians for a closer look at the wedges. DQ means they're very skinny. But widen them out to see how they look so we can add them up 3 methods with triangles, followed by a more traditional approach. Why? Because you've seen this type of integration many times before. Y as a function of x. Heights added from x equals 0 to r times 4. A bit complex. Let's change the coordinates and substitute and use the double angle formula and integrate. Great. Fast but great. Before we zoom in, a closer look at ds, which is r d theta, and dr, that's dA. Add up this area from 0 to r, and then swing it around from 0 to 2 pi, a double integral. Nice, but the final derivation is short. A circle, circumference 2 pi r, becomes a ring of width dr. Note, little r is free to vary like it did here. Big R is the limit, easy as pi r squared. Now, the surface area. Can we cover the sphere with triangles? Not these triangles, no way. These curved pieces will stay curved, and it doesn't matter how skinny they get. But I noticed something odd. This 4 pi r squared thing, factored, gives the lateral area of the cylinder surrounding the sphere, which is kind of hard to even say. To see how it works, we'll need spherical coordinates. Z is pretty easy. A projection next onto the xy plane, a point on the surface, swept out. dA, and all its details. Just go with it to see how these segments of the sphere can be projected onto the cylinder. Sine phi does the work. Different sides, but equal areas. Up here in the north, phi is small, and the sides are slim. Down at the equator, phi is 90 degrees, sine phi is 1, and the areas perfectly match. QED. Now back to line integrals on this circle. Wait, I thought that was a sphere. It is, but break it in half because we are on the xy plane. Z is 0. A piece of circle ds wrapped around the z-axis is a new circle. The idea here is better than the picture. This circle is this, the one where z equals 0. The purple circle is different. Is that purple? It's different. It's on the sphere and parallel to the xz plane. Its circumference depends on x. Hold on. As you go around the red circle, x changes, doesn't it? Well, yes, it does, but the magnitude of the red circle radius, it changed from purple to red, the magnitude of that circle's radius is x from here, where z equals 0. Next, a circle becomes a ring with width ds, many rings in fact, half of the total number, ds. Differentiate, change coordinates, and wait again. What happened to those fancy spherical coordinates? Aren't we on a sphere? We are, but we are also on the xy plane. That's where z is 0. That's where we defined x and ds and even dy dx. So we're good. And eventually, we are ready to rewind all the way back to this step here. Because if you are asking about ds, I know of a shortcut that will take you to the same destination. Next and last, finally, returning to spherical coordinates with the z and a projection into the xy plane, and dA is r d phi times r sine phi d theta. Integration is all you need. Next, pump up the volume, starting with another failed attempt. This bad idea was my idea. It was to take a half circle with some width here and then spin it around the z-axis, but it failed. Know why? Because d theta is a lie. The wedge thickness can never be flat. It can never, even if it's tiny, it can never be just d theta. It's not flat, so we're back to the drawing board and a point on the xy plane. Another circle, we have seen this before, and this time we want area pi x squared. A disk with height dy, you know what comes next: integration, multiplication, but no substitutions or coordinate changes will be needed. From disks, next to shells. Surface area is 4 pi r squared, and shell thickness is d. Are you ready to add them up from 0 to r? One final derivation, sorry about all the puns, but brute force with spherical coordinates. dA now popped out to become dV. A triple integral, but nothing we haven't seen and done before. Nothing too bad at all, leading to the question, was any of this necessary? No, it wasn't. It was, however, a convenient way to introduce, to test out, and to show off a variety of integration techniques.